Okay. All right. We're slightly behind, but it's not a big deal. Need to mop up from all these, the rest of Sturm-Liouville theory. So, okay. All right, so fill in 6.4. And to be a little more precise, properties of Sturm-Liouville Eigen stuff. So eigenvalues, eigenfunctions, eigen whatever. Okay. And I just actually, only had a couple properties left. So first, Rayleigh quotients. So recall that the eigenvalues for the form either an increasing or a non-decreasing sequence, so lambda 0, lambda 1, etc., and they keep increasing, possibly multiplicity 2. And this time, right now, we're going to focus on the smallest eigenvalue. So lambda 0 is the smallest eigenvalue, but it goes by a couple of other names. It's also known as the principal eigenvalue. Also called the ground state energy. Okay. And then B0 is called, therefore, the principal eigenfunction. And that satisfies, so your Sturm-Liouville operator applied to B0 is lambda 0 R B0, where R is, as usual, your weight function. Okay, so we look at approach another characterization of the smallest eigenvalue and the principal eigenvalue and its principal eigenfunction. Okay, so what is a Rayleigh quotient? And notice, so not Raleigh quotient, as some people say it. It's not Raleigh, North Carolina, so there's a Y in there. Yes, Rayleigh quotient is defined as, so it's an operation applied to a function, u, and it's just the inner product of u with LU, and this is a standard inner product. There's no weight function here, but it's divided by this inner product of u with itself, and that one does have a weight function r. So I can write this in integral form. So top of the integral from a to b of u LU dx over integral from a to b of u squared r dx. So, and therefore it's necessary that u be non-zero. It can be zero at isolated points, but it should not be zero altogether. So as long as that happens, this is well defined. Okay. And now that we have this, we have this proposition, which I'll prove momentarily. Your principal eigenvalue satisfies this relationship, which is called either a variational principle also known as a Rayleigh-Ritz formula. Okay. And it's actually quite a simple one. the principal eigenvalue is the nth. Also, in other words, the informally you can think of as a minimum, but it's not really the same thing. So it's a greatest lower bound of the Rayleigh quotient, where u is from where u is taken to be any function in this set v, which I'll define. V is a set of all functions that are twice continuously differentiable on the interval AB, and it has to satisfy whatever boundary conditions you have. This is for a regular Sturm-Liouville problem, not periodic. So we have these boundary conditions at A and B. Okay. All right. So this is for, I want to emphasize this, regular Sturm-Liouville problems. So the smallest eigenvalue is just the absolute, again, I can't really say minimum, but greatest lower bound, or infimum of Rayleigh quotients of all functions that really can be considered, but functions that you can substitute boundary conditions and have them satisfied, and also functions that you can substitute into the ODE, for Sturm-Liouville problem. Okay. All right. Now, so the textbook, and therefore my notes, only talk about using a Rayleigh quotient to characterize the smallest eigenvalue. But I do want to mention, as an aside, that if you go ahead and obtain the smallest eigenvalue, which has multiplicity 1, because it's a regular Sturm-Liouville problem, and then find a corresponding eigenfunction, if you then consider all functions u in this space that are orthogonal to that eigenfunction, and then you minimize the Rayleigh quotient again, you get the second eigenvalue and second eigenfunction. And then, if you consider all functions in space that are orthogonal to both those, then you can find the third eigenvalue and so on. So Rayleigh quotient minimized over the whole space gives you the principal eigenvalue and eigenfunction. But Rayleigh quotient minimized over a shrinking subset, or subspace, if you will, where you keep orthogonalizing against the eigenvalues, you keep orthogonalizing against the eigenfunctions you already have, will return more and more eigenvalues and eigenfunctions. So it really can be used to obtain several elements of a basis. So the textbook doesn't really get into this, but I remember learning this in the PDE classes I took at Stanford, so I wanted to bring that up here. Okay. Now, I also want to mention this Rayleigh-Ritz formula. So the Rayleigh-Ritz method is a method for solving eigenvalue problems such as the Sturm-Liouville problem, where you're trying to find approximate eigenvalues and eigenfunctions or eigenvectors, if you're dealing with a matrix, over a limited subspace. In my other class, 461, 561, very last topic we're going to cover is solving, is the Rayleigh-Ritz method for solving boundary value problems such as a Sturm-Liouville problem. So Rayleigh-Ritz approach, where you try to solve eigenvalue problems by limiting yourself to a small subspace and approximating from there, is a very important idea that spans not just analytical PDEs, but numerical methods. So you guys are who are in both classes are going to see it from 2 points of view. Okay. So I'm going to go ahead and prove this that by minimizing a Rayleigh quotient, we actually get the smallest eigenvalue. Okay, so if I go ahead and have general function u in this set, so it's non-zero, and I plug that into a Rayleigh quotient. So now instead of expressing these inner products as integrals, like I did earlier, I'm going to replace u by its orthonormal expansion in the space of piecewise continuous functions. So u I'm going to write as a sum. Actually, this is quite cluttered in my notes, so hopefully it's clearer here. Bm. And then I apply L to the same thing. But over here, I'm going to use a different letter for my index, just to avoid ambiguity. And then same thing down below. Oh, this time I have no L, just U itself again. With the weight function R. And recall, okay, so Vm, so Vn are orthonormal eigenfunctions for this Sturm-Liouville problem. So that means that L of Vn is lambda n R Vn. Also, the coefficients, so U is this orthonormal expansion. So each Vn is the inner product of Vn with U with the wave function R. So that, it's important to keep that in mind. Okay. Now, if we use the various properties of inner products, we're going to use a linearity. So, so the inner product of a sum is sum of inner products. Also, we can pull out constants. Okay. Now, our eigenfunctions are taken to be real, and we'll take U to be a real value function as well. So everything here is going to be real. Oh, actually, I do complex conjugate, so no biggie. All right. So now, by pulling the sums out of the inner products, above and below, I'm going to have AM complex conjugate, AN, and then I'm going to have inner product of VM with LVN up top, and then down below, same idea, pull out the sums, and I have AM conjugate, AN, and then I have inner product of Vm with Vn with wave function R. Okay. Now, LVn is lambda RVn. So what I'm going to get up top, I'll have these coefficients, and I'm going to have inner product of Vm lambda n RVn. However, I can go ahead and use the properties of the inner product. I'm going to take lambda n and pull that out. So I have lambda n here, Vm RVn. However, R is my weight function, so I can instead move the R down here. So instead of inner product of Vn with RVn, standard inner product, it's just Vn with only Vn with the R inner product. Okay, so using the operator L simplifies to this because these are eigenfunctions.
So then maybe not just be left to lambda n.
What?
Because the top will just look like the bottom.
Well, careful, it's a different n.
Oh.
Yeah, so
Oh,
not
so
not
they
yet,
won't
not yet. Okay. Okay. All right, so then we have the same thing down below, almost, except for these eigenvalues. Yeah, if all the eigenvalues are the same, then yeah. All right, but yeah, same inner product, same coefficients. Now let's use the fact that the eigenfunctions are orthonormal. So all of these inner products will go away, except when m and n are equal, in which case they'll equal 1. So now this simplifies drastically to just a sum over n of absolute value of an squared, if I have lambda n up top, so really dramatic simplification. And then I have a sum of absolute value of an squared down below. Okay. And yeah, so still can't cancel. However, all the eigenvalues, so this is a regular Sturm-Liouville problem. So all the eigenvalues form a, yes?
Why, again, when he asked about canceling on the left, how couldn't you do that?
Oh, well, for instance, okay, I could pull lambda n out as far as, well, actually, no, I can't. I can't pull it out at all.
Because there's sums. Never
Because
mind.
there's sums, yeah.
Sorry.
But now I'll get to a point where I can do some cancellation by saying, because keep in mind, the eigenvalues form a monotonically increasing sequence because it's a regular Sturm-Liouville problem. So I can say this is greater than or equal to, and I can replace lambda n by lambda 0. And now I can cancel. So this is greater than or equal to lambda 0. So lambda 0 is a lower bound for the Rayleigh quotient. But what have I not yet established?
That is the greatest.
Yeah, I need to be the greatest lower bound possible. The easiest way to do that in this case is the following. I'm going to choose a specific u. I'll choose u to be the principal eigenfunction, v0. Then my Rayleigh quotient is going to be, I'm going to run out of room. So it's inner product of v0, L of v0 over v0 inner product of itself with the weight function r. But then once I substitute, that is equal to inner product of v0 lambda v0 with weight function r over v0 with itself with weight function r. So I can pull the, whoops, that's lambda 0. And once I pull lambda 0 out, I have these two inner products that cancel. So we actually have equality. So in fact, the Rayleigh quotient not only has the greatest lower bound, when you're dealing with orthonormal expansion, it actually has a minimum. So when you're dealing with a complete space, you can show that, as I just did here. So not only is it a lower bound, it is the greatest lower bound that you can have. Just because we show that Rayleigh quotient actually assumes the value lambda naught. And that's it. So by minimizing a Rayleigh quotient, we actually get the smallest or principal eigenvalue. Okay. So questions about these manipulations? Okay. Now, here's another way that the Rayleigh-Ritz formula can be rewritten using integration by parts. So lambda naught is this Rayleigh-Ritz formula, which can be written in integral form, as integral a to b u times L of u, which is going to be minus p of x u prime minus u q of x u dx over integral of u squared r dx. So I've just filled in what the Sturm-Liouville operator L of u is. And using integration by parts, with this right here being the dv, what you get is, so we have integral of, so in this case, for integration by parts, your u is just u. Okay. So the integral that's left over is going to be p of x u prime squared, and then minus q of x u squared dx. And then in its boundary term, it's going to be minus p u prime evaluated a and b. I mean, you still have the same thing down below. Okay. Now, why this is important is for a regular Sturm-Liouville problem, which I need time to write Sturm-Liouville, so I'm calling it SL. We already have the assumption that our coefficient p is positive. So this is a built-in assumption here. But if I make some additional assumptions, so if your other coefficient q is non-positive, so less than or equal to 0, which actually does happen in some important applications like heat equations and wave equations, and this boundary term, pu prime, evaluated at a and b, is also less or equal to 0. But that says that the all of the eigenvalues are non-negative, because we'll find that lambda naught is non-negative, but that's the smallest eigenvalue. So all the other ones have to be non-negative as well. And there's something else that, so in fact, this is actually true for our standard boundary conditions. Dirichlet, Neumann, and periodic boundary conditions. In the periodic case, this term will again be zero. So in all three of those boundary conditions, generally, normal, and periodic, this term is actually equal to 0. So you just ignore it. And we generally get for Dirichlet boundary conditions, you actually have the eigenvalues being strictly positive. You can't have a 0 eigenvalue for that case because it leads to a solution that's 0 altogether. Okay. Now, with lambda not being the minimum value of a Rayleigh quotient, if you plug some other but it assumes at minimum when you plug in the principal eigenfunction. What if you don't have a principal eigenfunction? If you plug in any other function, you can at least get an estimate, approximation of a principal eigenvalue. So we'll take a look at an example. So our usual constant coefficient problem with Dirichlet boundary conditions. Okay. Now, in this case, we know what the eigenfunctions are. So this is on the interval 0 to 1. So the eigenvalues are, okay. Well, actually, I started numbering them. Normally, for this problem, I start numbering from n equals 1, but I've been using n equals 0 the whole time. Okay. So these are all our eigenvalues, and then the eigenfunctions. Okay. So that means that our principal eigenvalue is pi squared, and that's roughly 9.87. Okay. So what I'm going to do is I'm going to plug in a different function that still satisfies the boundary conditions into Rayleigh quotient, and what we get is so I'm going to let u of x equal x minus x squared, and I chose that one because, of course, the factors x times 1 minus x, and this is equal to 0 on the boundary. Because to minimize the Rayleigh quotient, you have to consider only functions that satisfy the boundary conditions. So this would be one of the simplest, actually this is the simplest polynomial function that satisfies the boundary conditions. So, I plug this into Rayleigh quotient, and see what we get. So that's going to be the integral from 0 to 1 of x minus x squared with our Sturm-Liouville operator applied to x minus x squared over x minus x squared squared with a weight function of 1. So r is 1 in this case. And the Sturm-Liouville operator is minus u double prime. Let's see, actually, yeah, that is the whole Sturm-Liouville operator. Because in other words, we have minus u double, our ODE is expressed this way, minus v double prime equals lambda v. The idea is you make the right side equal to lambda rv in your ODE. Everything else that's on the left side, that's your Sturm-Liouville operator. So that's the convention that I'm using. Okay. The textbook likes to put the minus on this side. Why, I don't know, but whatever. So in this case, we're just taking minus the second derivative. So that's going to give us 2. So we're going to have integral of 2 times x minus x squared from 0 to 1 over x minus x squared squared from 0 to 1. kind of tedious to work out, but get a nice number in the end. It's 10. And sure enough, that is greater than or equal to the smallest eigenvalue, lambda naught, which is roughly 9.87. So what we get here is, think about this. Your principal eigenfunction is sine pi x. So sine pi x has this kind of a graph. Starts out at 0, ends at 0, when x is equal to 1. But our function we tried, our u, x minus x squared, has similar behavior. It's a downward-facing parabola that's equal to 0 at the same points. So it's no surprise that the Rayleigh quotient of that function, which kind of resembles this function, gives you a decent approximation for the principal eigenvalue. Okay. So the Rayleigh-Ritz method proceeds by, you have some function like x minus x squared serving as an initial guess. And then you use it as a starting point and you build a sequence of orthogonal functions using the operator L. And as a result of that, you can actually compute the minimum of a Rayleigh quotient over that whole subspace of functions that you keep building. And the smallest of those, of the eigenvalues of that matrix, is your approximate principal eigenvalue. So actually, yeah, instead of just talking about it, I'm going to explain it a little bit further. Okay. Okay, so actually this is something I recall learning about in my analytical PDEs class way back in 1992. This is a Rayleigh-Ritz method for approximating eigenvalues.
That's the year I was born.
Oh, alrighty. Oh yeah, both of you. Okay.
I was 2 years old.
Ah.
I was 11.
Okay.
Yeah, because we're now dealing with students that were born in like 96 or 97.
Right.
And as soon as I started having students that were born in 2000, that's going to really weird me out. Okay. So you choose functions, I'll call it u naught. And what you do then is you compute the norm of this function using the R inner product. So inner products of, I need to use UK minus 1. With the weight function R. So think of it as a denominator in your Rayleigh quotient.
Is that a beta or a B, or does it matter?
It's a beta. Okay. And then, let's see. So then VK will be like a normalized version of this of this latest function. Then what I'll do is I'm going to apply the differential operator, my Sturm-Liouville operator L, to this function, and then take the inner product, the standard inner product, of VK and WK, which is equivalent to that, which is the numerator of your Rayleigh quotient. So basically, so in fact, this is alpha k is equal to the Rayleigh quotient of VK, which is also the Rayleigh quotient of UK minus 1. Because if you're scaling a function, that does not change your Rayleigh quotient. In other words, if you're normalizing, yeah, if you're scaling it, it's not affected. Okay. Then I take so then I go ahead and carry out this recurrence relation. So UK is equal to WK minus alpha k VK minus beta k minus 1 U VK minus 1. I also V0 should equal 0, so that all the formulas actually make sense. Okay.
Dr. Lambert,
Yes.
is that first one supposed to be beta k minus 1, or where is that coming from?
Yes. It is. Okay. Yeah. Okay, and this is the whole algorithm, but then what you do is your approximate, at each iteration you can compute an approximation of your principal eigenvalue. And it is the smallest eigenvalue of this matrix that has the alphas along the diagonal, and then the betas above and below on the subdiagonal and superdiagonal. Okay. Now, does anyone in this room recognize this iteration that's I referred to by a different name in other contexts?
It's yes. I recognize what it looks like, so we did it at 610, didn't we?
Yes, we did.
Off diagonal, when the super diagonals and the off diagonal, I'm not saying off diagonal, the lower diagonal.
Tridiac, no.
It is tridiagonal.
Yeah.
Yeah.
I was gonna say I
Oh,
recognize the
try.
pattern.
Yeah.
Yeah.
Okay.
It's a little bit on 50,
Yeah.
561, like,
Yeah.
You
Um,
going for something else?
Yes.
well,
That's the start.
I want to see if anyone knows the name of the algorithm. Certain people in a certain research group should
Get a note straight.
Oh, are you talking about Lanchos?
Yes.
I was
Yeah.
gonna say, forget that.
Okay. Yeah, well, I guess because you haven't seen it since 610. It's been a year ago.
And I.
Yeah, but this also underscores what I brought up in the group cases group meeting today. That because, like, for instance, you and I haven't talked about Lanchos at all. You've had some exposure to it. You not yet. Yeah, so it's coming, but we just haven't got to that point yet. But
And I went out of that.
yeah. And like Amber D is very familiar with it. She would have recognized her off the bat, but she's not in this class. So.
Sorry, I didn't know what you were looking at the exact answer.
Okay. Yeah. Okay. Yeah, but I was hoping this would ring a bell to somebody as we went through it.
My bad.
Yeah. Okay. All right. So yeah.
How is Lanchos spelled again? Is it Lancazos or Lansco?
It's.
So,
Yes.
so this is
Does it
analog
matter?
Yeah, of course it does.
of the Lanchos algorithm.
When you get famous and someone misspells your name. Oh.
People misspell my name all the time.
For computing eigenvalues of a matrix. So
Lancazos. Okay, now it
Yeah.
help me remember. Okay,
Yeah.
see.
I
yeah.
was
So
gonna say, I knew it was weird.
so really you can think of Rayleigh-Ritz method as Lanchos algorithm generalized to more general linear operators. Like here we're using a Sturm-Liouville operator on a function space. Lanchos algorithm is generally described strictly as being for where here you have a matrix. So you approximate the eigenvalues of a large matrix through the eigenvalues, either smallest or largest, of a much smaller matrix. And the idea is, as you keep iterating, this matrix is going to get larger and larger, and your approximation to lambda naught will get closer and closer. It should converge. Now, how well it converges, of course, depends on the particular Sturm Liouville operator you're dealing with. But yeah, so as it goes to show, we're talking about differential equations or problems just strictly from linear algebra. A lot of the same methods apply because they all deal with linear algebra and vector spaces, whether it's Rn or function space. There's a lot of cross-pollination of all these ideas, and what I thought was quite nice from the classes that I happened to take at Stanford was I kept seeing these same things over and over again in different classes, and I started to tie them all in together, and it made it easy for me to apply perspectives from one subject area to another and help you understand all of it more. And that's why I try to do the same thing in these classes, and that is bring these ideas and again draw these connections. Okay. All right. So okay. All right. Now, what?
I thought you just said I still have an hour left. I was like, you don't.
Oh no, because the thing is now that I'm teaching both classes again, because Amber had taken the other one over for a while, I recall how exhausting it is to do these two classes back to back every Monday, Wednesday. Okay. Or at least mentally exhausting.
We can have a pizza party next week. Would that be fun?
Why next week specifically?
This is my birthday!
Oh, yeah,
Oh.
that's right, it was 18.
What day?
The 18th?
I just.
20th? Yeah, she just said the 18th.
Sure,
But still, his is on Wednesday.
Hey! We could have something on
Like we had
Monday and
double
something on
pizza party.
Wednesday.
Yeah, it's me and Adam's birthday.
Yeah!
Oh, okay.
So we should definitely celebrate.
Or eat.
I mean, at least something.
Yeah. I'll pick it up. Okay, so
Shouldn't be any debates.
the last property of Sturm Liouville Eigen stuff is that this is only for regular, so not periodic. For regular Sturm Liouville problem, the nth eigenfunction Vn has exactly n zeros in the interval AB. So that's a quite remarkable property. I won't take the time to prove it here, but so for instance, what that means is the principal eigenfunction would not actually. Oh, sorry. It's supposed to be the open interval AB. So in the interior. So the principal eigenfunction, therefore, does not change sign within the interval. And I have to be careful about closed versus open interval. For example, the Dirichlet problem, we saw this eigenfunction it's right over there. Here, sine pi x for a Dirichlet problem on 0, 1. Okay, you have zeros, but these are at the endpoints. But there are no zeros in the interior, so the eigenfunction is of one sign throughout. And as you go to the next eigenfunction, you'll have one sign change within AB, and then two sign changes, and so forth. Okay. And really, this is a consequence of the orthogonality of the eigenfunctions. In fact, so what most of you who take 772 in the fall. We deal with orthogonal polynomials, and it's actually quite easy to prove for polynomials, because they're much nicer, that orthogonal polynomial of degree n has exactly n zeros within the interval of which it's an orthogonal polynomial. So I haven't seen the proof for this property here, but I imagine you use a similar idea, that basically what you're doing is you're assuming that this function has a certain number of sign changes, and if you assume that the number of sign changes is greater than n or less than n, you get some sort of contradiction. And therefore it has to be exactly equal to n. And the reason why it can't be the other possibilities has to do with the orthogonality. Okay. So this gives us an insight into the graphs of these eigenfunctions. Okay. All right, so that's the end of this very long section, 6.4 properties of Sturm-Liouville Eigen stuff. So now during the rest of the time, I can get started on the next section. Because we've been looking at homogeneous Sturm-Liouville problems. But just as we dealt with a non-homogeneous wave equation, we can make these non-homogeneous as well and still solve them. And everything we've learned about the eigenfunctions will help us do that. All right, so at least I should be able to get through the main idea today, and then the examples might have to wait till Monday. All right. But yeah, it does feel like I spent forever on this chapter. Okay. So, what I have here is for the, okay. Look at a parabolic problem. And I've written this form down before where we have more general coefficients, because the idea is sufficiently general. So we have our Sturm-Liouville operator. And now we have a non-zero right-hand side, big F of x and t. And we're going to focus on the regular Sturm-Liouville problem as opposed to periodic. Okay, so our boundary conditions, we'll work with the usual general boundary conditions. Okay, so we have alpha u a plus beta u prime of a. So the boundary conditions are still going to be, slight typo in the notes. Okay. So the same homogeneous boundary conditions A and B. Interesting enough, the next section, which we'll likely get to on Monday, we'll deal with non-homogeneous boundary conditions. Whoops, sorry. We're back dealing with PDE, so it's U of AT and U BT. So I can't forget the T anymore. Okay, so we have these regular boundary conditions satisfied, and then we have our initial condition. Okay. So, like before, we apply separation of variables. But only on the homogeneous PDE. We can't use separation of variables with the non-homogeneous one. So we work with big F being 0. And what we get are the usual, so we get a usual Sturm-Liouville problem. So we have P of x, V prime plus Q of x, V plus lambda R of x, V 0. Okay. And we also get a time-dependent ODE, but we're not interested in solving that yet, because we're going to solve a time-dependent ODE based on the original PDE that we're working with in the first place. And then we have our boundary conditions for a Sturm-Liouville problem. Okay. And so we assume that we're able to solve this Sturm-Liouville problem to get our eigenvalues and eigenfunctions. So all of this is our, as I've been referring to today, eigen stuff. Okay. Now, little LaTeX issue to fix here. Expressions look rather funny when you have infinity and you forget to put the backslash. Okay. So once we have our eigenfunctions, we take eigenfunction expansions of a couple of items. Okay. So we have our initial data has an eigenfunction expansion with coefficients Fn. So Fn is the inner product of Vn with R, Vn with F, with wave function R. And then we also take a eigenfunction expansion of big F, our source term from our PDE, but we divide it by our wave function R of x. So we have this eigenfunction expansion. And we have, okay, this is big F, but this is a function of t, because big F depends on t, therefore the coefficients have to depend on t. And these coefficients are the inner products of Vn with big F, but the standard inner product. Notice there's no weight function here. Or you can think of it as there is a weight function, but we're taking inner product with F over R, so the two R's cancel out. Okay. So things work out more conveniently if you define the inner products in this manner. Okay. Now, okay. So in fact, I will write it this way as an alternative. So Vn with F over R, R. Okay. So still, you still think of it as an expansion orthonormal eigenfunctions. Okay. Now, I also need an expansion of my solution. So, okay, how much time? All right. Okay, so we have our solution will be expanded also in the spaces of eigenfunctions. So we have our coefficients, which we'll call an of t times bn of x. Basically, it comes about by separation of variables. And each an of t is an inner product of bn with u with the wave function r. And we need that to ensure orthogonality. Okay. So now what we do is we substitute all the expansions into the PDE. Okay. Now, let's go ahead and do that. I haven't done it here in the notes, but I'll do it here. So we have r of x, m of t, and then I have, expansion for du dt. So that's going to be a sum a n prime of t dn of x. Okay. Then I have minus of x. Well, actually, I can just simplify this. I'm going to have plus the operator L, or determinative operator L, applied to the expansion for U. That'll simplify things greatly. And all of that is equal to, I can have the expansion for big F. So that would be Fn of t dn of x. Okay. Let's see. The other thing I'm going to do is, before I go any further, I'm going to simplify this because Vn are eigenfunctions. So this is equal to the sum of An of t, lambda n, Vn of x, R of x. So the weight function has to be included in its eigenfunction eigenvalue relationship. So I have R of x throughout on the left side. And I'm going to write this as, well, actually, okay, I'm going to leave it like that. Okay. Because I want to at least have an R of x throughout. Okay. Actually, probably a better thing to do on the right side is not yet fill in the eigenfunction expansion on the right side. Divide by R of x and then multiply by R of x for what's coming next. So now what I can do is take the inner products with Vm of x. So I pick one eigenfunction Vm, take the inner product, and I should say the standard inner product, because we don't use a weight function R for this inner product because R is already there. Then we can express them as inner products with a weight function R just a little bit. So in other words, what it means is I'm going to multiply by Vm and integrate. So I have R of x, okay, so integral. I'm going to pull out sums. Okay, so I have, actually I can do better. I can leave m of t out here. And prime of t, and then I'm going to have inner product of Vm with Vn with weight function R, so this R gets absorbed into here, plus some An of t lambda n, and then I have inner product of Vm with Vn again with weight function R. And then on the right side, I'm going to multiply by Vm and integrate. So okay, so I have f of xt over R of x, Vm of x, So this is the inner product of F with Vm, the standard inner product. Okay. Now what happens is we take advantage of orthogonality. All these inner products go away except when m equals n. So I get m of t a n prime of t plus lambda n a n of t, and this inner product on the right side becomes fn of t. So this is the ODE that I solve for n equals 0, 1, 2, etc. So I've changed my PDE into a family, a one-parameter family of ODEs. And these are first order ODEs to solve. And then I have my initial condition, an of 0 is fn. That comes from my eigenfunction expansion of the initial data. All right. Now, the nice thing about this is, okay. Yes?
When you have written over there standard inner product with Vm of x, what's that pointing to or describing?
At least to this.
That part.
Yeah. Okay, so. All right. Now, the nice thing about these ODEs, we can solve them. Now, we would have to express the solutions as integrals because m of t and big Fn of t can be anything. But at least we have a solution formula, something that you would have learned from your first differential equations course. Okay, so yeah, I'll definitely hold off on the examples until Monday. Whoops. Okay, still recording. I had the mouse hovering over the stop button. That could have been bad, but nope. Everything's fine. Still working. Okay. So the solutions of these ODEs, we have an of t is e to the minus lambda n integral from 0 to t of 1 over m of s ds. So this is the integrating factor. Actually, 1 over the integrating factor that you actually use to solve this. And this is multiplied by the initial value, little fn. And then you have the same integrating factor again times the integral from 0 to t of e to the lambda n, integral from 0 to tau times big F n of tau divided by m of tau d tau. Okay, because basically in the ODE, the first thing you do to solve it is you divide through by m of t. And then you use the integrating factor method from there. Okay. So, yeah.
So fn of tau over m tau is, timed with e to the power of that, right?
Yes.
Okay.
Yeah. Okay.
I know that says integrating factor. What's the 1 slash?
Oh, it's not the actual integrating factor. It's 1. Actually,
One.
I'm going to step through this so you can see where the solution.
I know, like that's e to the negative power, so that would be 1
Yeah.
over that.
Because if you have
So that's
m of
what you just
t
mean by that.
Well, okay. I'll do steps anyway, just because.
Okay.
So if you divide through m of t, you get an prime of t plus lambda n over m of t an of t equals big Fn of t over m of t. And from this coefficient right here, that's where you get the integrating factor. So your integrating factor is, I'll call it mu of t, is e to the integral of your integrating, of your coefficients. So what that means is you have integrating factor prime of a whole thing, because this is, by multiplying through by integrating factor, you have product rule in reverse to get to this point, and on the other side you have integrating factor again times the right side. Okay, but now what you do is you integrate, because it's thus integrating factor, both sides from 0 to t d tau. But that means that everything on the inside has, any t has to become a tau. So you're changing letters. And here you're integrating a derivative, so as a result of the integration, you're going to have just plugging in the limits into that. So you have the integrating factor, still with t, minus the integrating factor with 0 plugged in. So in fact, so right here, this is also tau, but then you plug in the limits 0 and t, so then you get, your integrating factor becomes 1, because you're integrating e from 0 to 0, times an of 0 equals this integral, 0 to tau, okay. Now, an of 0, that's Fn. That's the initial condition. And now, you take this whole thing and you solve. At this point, you're just rearranging. You solve for an of t, and that gives you that. So it's basically a review of integrating factors from 285, of how all that works. And now I'm out of time. So, okay, actually I have 1 minute, and I have one very quick thing to say. All of this is for a parabolic problem, like the heat equation. If you have a hyperbolic problem, so your ut becomes utT, that's the only change in the PDE. It's the exact same process, but you solve second order ODEs, so m of t an double prime of t plus lambda n an is equal to Fn. And then for that kind of PDE, you're going to have 2 initial conditions, like u is equal to f and udt is equal to g, like from chapter 4. So you have expansions of both those initial data that give you your 2 initial conditions for this ODE. Okay, so that's the only difference. And now I really am out of time. So I'll, you have, one really long and ugly example of this on Monday. So, yay. Yeah.